Hello, this is Dan List, and today, for our Calc 3 final review, I'm going to be going over how to get the first and second degree Taylor polynomial for the following function. F of xy equals e to the x squared plus 2x minus y. And that's going to be for an xy near the point 0, 0. So, here's how we attack the problem. First order of business is to take the partial with respect to x of the function. So we get 2x plus 2 quantity times e to the x squared plus 2x minus y. And I have distributed that. You'll see why later for ease of second partials. The partial with respect to y, which is fairly easy, negative e to the x squared plus 2x minus y. And then we take the second partials. So here's our second partial with respect to x and respect to x. And as you can see, this is why I chose to distribute in the partial with respect to x. It made it a little easier to attack the partial here. So we have quite a lengthy term. 2x times the quantity 2x plus 2 times e to the x squared plus 2x minus y plus 2 to the to the 2e to the x squared plus 2x minus y times 2 plus 2 times the quantity 2x plus 2 times e to the x squared plus 2x minus y, which is a little cumbersome, so we can certainly spend a little time distributing and combining our like terms to simplify our partial with respect to x and respect to x to get the quantity 4x squared plus 8x plus 6 times e to the x squared plus 2x minus y. Then we need our mixed partial, negative quantity 2x plus 2 times e to the x squared plus 2x minus y, and our partial with respect to y and respect to y, which interestingly enough is the same as our original f of xy function. And then going back to the problem, we pointed out that we're looking to use these Taylor polynomials to approximate our function at locations near 0, 0. So our next order of business is to take all of these first and second partials and plug in those xy values to help us towards getting the first and second degree Taylor polynomials. So the partial with respect to x, when we plug in 0, 0, we end up going through the process, and 0 is nice to plug in. It certainly eliminates a lot of issues, and it reduces down to 2. And the partial with respect to y reduces down to negative 1. The second partial, the xx partial, reduces down to 6, and again, much more manageable than our simplified form. Certainly we could have done it in the other form, but it's a little more difficult, at least more cumbersome. Our mixed partial, when we plug in 0 and 0, we get negative 2. And when we evaluate our second partial with respect to y, we get 1, which we don't have to replicate the work, but we should note that evaluating the function at 0, 0 is also going to give us 1, because we noticed earlier that our second partial with respect to y was the exact same as our function. Alright, at this point we can start looking at creating our first degree Taylor polynomial. And there is the general formula for it. Of course, we want to get more specific, so we plug in our a and b values, our 0, 0, and we've evaluated all of those previously, so we just have to plug those values in now, and we get L of xy equals 1 plus 2 quantity x minus 0 plus negative 1 times the quantity y minus 0. And we can simplify and make that a little nicer looking. And it turns out our first degree Taylor polynomial is 1 plus 2x minus y. Alright, on to the second degree. The second degree looks a little more complicated. It uses the first degree Taylor polynomial in it, and on top of the first degree Taylor polynomial we also add the second partial with respect to x over 2 times x minus a squared plus the mixed partial times x minus a times y minus b plus the second partial with respect to y over 2 times y minus b squared. Again, we can plug in our a and b values here of 0 and 0, and we've evaluated all of these previously, so we can just plug them in and we get this. And again, we can simplify it a little bit. We have one term with a 6 over 2 and some parentheses, and we can get rid of all of that and clean it up nice and neat and get 1 plus 2x minus y plus 3x squared minus 2xy plus 1/2 y squared. So that is our second degree Taylor polynomial. Now let's take a look at the computer and confirm that. So here is the computer, and as you can tell, sorry it's a little choppier, I have inputted in our three functions. So I will click on the first function and graph it. And as you can see, we have a fairly interesting graph. Zoom around a little bit. And at this point, we should go to graph. Where is it? There it is. Add a point. And we want to look at the point that we're considering here, which is going to be here, 0, 0, and it was evaluated at 1 if you recall. So 0, 0, 1. And I want you to be able to see it, so I'm going to make it nice big point. I'll make it black. And you can see there's our point. There's our nice big point. Now, let's go over here and also graph our first order Taylor polynomial, which, as you can see, is a plane, and that plane is touching the point, and looks like it's at least reasonable base approximation of our function at that point. Now let's go back, and instead of the first, let's use our second degree Taylor polynomial, keeping that point active. Now you can see it's much more of a smoother fit. It looks like around that point 0, 0, 1 we have really matched up our function pretty well. So that second degree Taylor polynomial is acting as a very good approximation of that curve at the point 0, 0, 1. Alright, I hope this was helpful for your final, and good luck.